Um, okay, so just a brief disclaimer. So information presented is not an official opinion of Michigan State University or University of New England. So I'm Zach Burton. I was a professor there in the Department of Biochemistry and Molecular Biology for 30 years, now retired. Lei, my co-host, that's Lei, is at the University of New England, Biddeford, Maine. Okay, so the title of the presentation is Origami and Pseudosymmetry. And I'm Zach Burton once again from MSU, Department of Biochemistry and Molecular Biology, now retired. And Lei is a professor at the University of New England School of Biological Sciences, Biddeford, Maine. Okay, so origami and pseudosymmetry. And what I want you to take away from this, these are the subliminal messages that I want to sear into your brain. So RNA origami and pseudosymmetry, snapback primers, ligation is important in the ancient world. So this is because RNA exists in colonies. So similar RNAs and sometimes identical RNAs, and sometimes unrelated RNAs can be ligated together in the ancient world, pre-life world. And they're ligated, one reason to ligate them is to replicate them. And RNA colonies I'll describe include snapback primers, any 31 nucleotide mini helix. Mini helix is a snapback primer. And part of this is a puzzle that anyone can solve. And the solution to the puzzle, if you can't solve it, is the 331 nucleotide mini helix theorem. After you ligate things together and you replicate them and you replicate their complement, you have RNA processing to make back new RNAs to fill the colonies. But because ligation is involved, you also make more complicated RNAs. That's how tRNA came to be made. So we're going to talk about RNA origami, protein origami, and protein pseudosymmetry. I'm not sure that RNA origami is really the right way to describe this. It maybe is more like RNA macrame, but RNA isn't paper and it's not string, it's RNA, and it combines in ways that I can describe this way. If you translate it into protein, then you can fold it into a pseudosymmetrical barrel. I'll show you some of that. Notably cradle-loop barrels that are important for DNA synthesis and RNA synthesis, and also beta-alpha 8 barrels, which are also called TIM barrels, and these are a big part of sugar metabolism in modern life. And then also these can be refolded into beta-alpha 8 sheets, and that's the basis for forming Rossmann folds. So there's really interesting evolution that involves RNA, combinations of RNA by ligation, which we're going to call RNA origami. And this can involve complex folding and processing. And then protein origami when you translate it into protein, which gives you protein repeats. If you fold protein repeats, you get protein pseudosymmetry. And that's some of the most important features of ancient life. And you can then break the pseudosymmetry into beta alpha 8 sheets and get new products that are also of high value in evolution. So I'm going to present the 331 nucleotide mini-helix theorem. If you watch some of my other presentations, you'll have seen this already. This is the cheat sheet for the solution of the puzzle that anybody can solve. I'm going to show you that type 2 and type 1 tRNAs were generated as a replication and processing error of 31 nucleotide mini-helix replication. So you're trying to replicate these 31 nucleotide RNA mini-helices, and you do it by ligation, and you make a mistake in processing, and you get type 2 and type 1 tRNAs, which are new important features of evolution. Okay, so evolution of life on Earth, that's what's under discussion. But realize that once you generate tRNA, once tRNA can be chemically evolved, it's game over. You've evolved life. And the reason is that tRNA is a system that can teach itself to code and to generate the genetic code. Until you have a genetic code, you don't have life. You need a genetic code because you need diversity of protein synthesis to sustain living systems. So RNA origami, what do I mean by that? So this is how it works to make a type 2 tRNA. You can tell this is a type 2 tRNA because here you have this funny chicken wing coming off here. It's yellow and green segment. That's derived from a 3' acceptor stem. That's derived from a 5' acceptor stem. And this is called the variable loop or the V loop. Anyway, this is made by taking these little jump rope molecules. So this is a D loop, cherry flavored jump rope, if you like. And these are blueberry flavored jump ropes. And you ligate this one to two of these. And you generate, this is a D-loop mini-helix. It's got a 5' acceptor stem and then a 17 nucleotide core and a 7 nucleotide 3' acceptor stem. And you ligate it here to a 5' acceptor stem, 5' acceptor stem, followed by this blueberry flavored RNA, and then a 3' acceptor stem. And then you ligate another molecule that's identical to this molecule there. And in order to generate this molecule, so this is a replication intermediate for 31 nucleotide mini-helices. So you're trying to replicate, in this case, two of these and one of those. And I don't want to go through the whole process of that, but if you're a molecular biologist, you would be able to extract that information just by looking at the diagram. But basically, to make this molecule, all you have to do is make this short 9 nucleotide internal deletion in between these two red arrows. So what that does, 9 nucleotide internal deletion, it deletes 7 yellow and 2 green. And because this is 7, this is 5, so you're left with 5 green. And those 5 green are these 5 green right here. So if you follow the chain around, you have a 5' acceptor stem, and then a D loop, and a fragment of a 5' acceptor stem that corresponds to these 5 nucleotides here. And for the variable loop, you have 7 nucleotides of yellow plus 7 nucleotides of green, a 3' acceptor stem ligated to a 5' acceptor stem without any processing, and that's what makes the chicken wing here. So type 2 tRNA was made by RNA origami. It was made by an attempt to replicate these 31 nucleotide mini-helix. molecules by ligating them together, copying them, and then processing them out. So you can either process them into more mini helices by processing there and on the ends, and you get more of these, or you make a mistake and you process here and you get this. And this is an advance in chemical evolution because this is a molecule that can teach itself to code. Much can be said about type 2 tRNA, and I think I won't say it here. I'll say it in another presentation sometime. But it is a beautiful molecule. It's quite an important molecule. And then type 1 tRNA, so most tRNAs are type 1, they're not type 2. But type 1 tRNAs are almost identical to type 2 tRNAs. The only difference is in this segment here. So this segment here is only 5 long. But if you back up, that segment here is 7 yellow and 7 green. And if you bump forward, it's just 5 yellow. So you deleted 2 yellow and 7 green. And that event is very similar to this deletion here. So right here, you have 7 nucleotides plus in yellow plus 2 in green, and that's a deletion of 9. And you're left with 5 green. These 5 in green that correspond to these 5 in green here. And on this side, you have a 9 nucleotide deletion between these 2 red arrows. 7 nucleotides green disappear and 2 nucleotides yellow, and you're left with 5 nucleotides yellow. That's this fragment right here. And just to compare it once more, here you have 7 yellow, 7 green, and here you've deleted 2 yellow plus 7 green, and you're left with 7 yellow. Sorry, 5 yellow. So RNA origami generates type 1 tRNA and type 2 tRNA, and it involves ligation of similar and sometimes identical molecules, and then processing at this position and that position by internal 9 nucleotide deletions to generate type 1 and type 2 tRNA. That's a type 1 tRNA, and it's quite a beautiful molecule. And it's completely important molecule in terms of evolution of life on Earth. Without evolution of this molecule, you don't get life on Earth. There aren't a million different ways of solving this problem. There may be other ways of solving it that we don't know about, but this is the only way that we know of to solve the problem of evolving life on Earth or life on another planet. This is the same demonstration, but shown as sequence. Okay, so you have polymer world going to mini helix world, going to tRNA world. tRNA world is type 2 tRNA, type 1 tRNA. Comparing this molecule to this molecule, the only difference is in the variable loop. Here you have 7 yellow plus 7 green. Those 7 in yellow, that's a 3' acceptor stem. The 7 green, that's a 5' acceptor stem. So 7 plus 7 is 14. To make this molecule here, you have to delete these 9 here. So you delete 7 green plus 2 yellow, and you get 5 yellow that correspond to these 5 yellow right here, part of a 3' acceptor stem, and that's the variable loop. In type 2 tRNA, the variable loop is a 3' acceptor stem ligated to a 5' acceptor stem. So how does all this work? So in order to replicate mini helix world, you take this 31 nucleotide mini helix and you ligate it to that, and you ligate it to that. And so you get this molecule here, and you can add a snapback primer, and you can replicate eventually around in a circle. And then you can process into more mini helices by processing there, and now you get more of these back. But if you process by this internal deletion, you get a type 2 tRNA. And if you process here and here, you get this molecule. This deletion and this deletion are related to each other. They'd be identical on opposite RNA strands, complementary RNA strands. That's not necessarily how it occurred, but this deletion is closely related to that deletion in pre-life evolution. And everything shown here is chemical evolution because this molecule and this molecule isn't enough to generate life. You need complete tRNAomes and a genetic code to get the living organisms we recognize today. And much more can be said about this, and it's probably said in some of our other presentations. So that's RNA origami, and it generates type 2 tRNA and type 1 tRNA. If you want to call it macrame instead of origami, please feel free. We're not sure what the right word for this is. We hope it's a good description. We hope our description is clear, even if our terminology is loose. Okay, just to give you an idea that what we're describing might be true. If you go to tRNA, one of the predictions of this model is that this 17 nucleotide fragment with stems of 5 and loop of 7 is initially identical to this stem loop stem here. So this is the anticodon loop of tRNA. This is the T loop. This is a kind of consensus of 46 Pyrococcus furiosus tRNAs, and it's presented as tDNA. So T in DNA represents U and RNA. This sequence is CCGGG. This is after 4 billion years of Darwinian evolution with this sequence and this sequence in the same molecule. So the sequence is CCGGG, CCGG, often G. This is 7-mer loop with a U-turn after a U. This is a 7-mer loop with a U-turn after a U. So I argue that this stem loop stem and this stem loop stem that form the anticodon loop and the T loop were initially identical. They're practically identical now. And if you take this segment here, that's also 17. And this sequence is initially UAGCC, UAGCC, U, G for A, GCC, UA. Initially, that was a UAGCC repeat. This sequence here is GCG, GCG, G, that's an acceptor stem, a 5' acceptor stem. And this is its CGC complement. This little 5 nucleotide sequence here used to be GGC, GG, it's only slightly changed. This little sequence as in GGC, GG there. This used to be CCGCC as in CCGCC there. So everything about the model, what we call a theorem, is accurate and true and correct. And is highly predictive for sequences of tRNAs in living organisms today. Okay, so origami, as we present it, is generating life out of smaller related or identical units. Pseudosymmetry uses origami. Origami generates sequence repeats, and those can be used to generate pseudosymmetrical barrels. So what we're doing here is building life by chemical evolution as if we were playing a child's building toy. And it's really quite a remarkable discovery, I think. And the reason that you use RNA origami to make RNA repeats and then protein origami through translation and then pseudosymmetrical folding is this is a fast means to complexity. So that's why it occurred. In times of really rapid evolution, origami repeats, RNA repeats, and resulting translation and pseudosymmetrical folding. This is often a strategy that wins. Not always, but often. So it's part of the times of most rapid evolution. And it describes a big chunk of the pre-life to Luca. Luca is the last universal common cellular ancestor. And also you see lots of pseudosymmetry and repeats generated during generation of eukaryotes, which is another process that involves origami and pseudosymmetry. Another time of rapid evolution. So we're talking about pre-life now. In an RNA-dominated world, you have similar or identical RNAs, and they're duplicated in RNA colonies, and they're duplicated by RNA ligation, linking RNAs together and making more complex molecules. So from many helices, you get transfer RNAs. And examples, the 331 nucleotide mini-helix theorem to generate type 2 and type 1 tRNAs, as I showed you. Beta alpha 8 barrels. These are the basis for sugar metabolism. And they've lasted on Earth for 4 billion years. Very successful folding of protein. You can take a beta alpha 8 barrel and refold it into a beta alpha 8 sheet. For instance, TCA cycle is generated from Rossmann folds. These are Rossmann folds. And double psi beta barrels can also be made by pseudosymmetrical folding. And that includes Pol D in archaea, a DNA polymerase, and also RNA polymerases, which are found in all organisms. So pre-life replication, you have RNAs in colonies, you have ligation, you require snapback primers, and any mini helix can act as a snapback primer. You have replication, you have complementary replication, and then you have processing, and you generate new molecules to add to colonies, but you also generate more complex molecules that become tRNAs and ribosomal RNAs and many other things as well. Ligation supercharges chemical evolution of complexity. So because you have ribozyme ligases in pre-life world, you generate much more complicated molecules. So this is an example of pseudosymmetry. It's a beta alpha 8 barrel, and it's beta alpha repeated 8 times. It's a pseudosymmetrical molecule. You can see that it's pseudosymmetrical. Basically, you have a 2-fold axis through here. If you made this into a circle, you could have an 8-fold axis down the center. And this molecule is found in chickens, but it was found in pre-life 4 billion years ago also. And this is Rossmann fold. And let's see, here we've rearranged and stretched out this pattern. So this pattern goes to this pattern. And so this is RNA origami going to protein origami, going to pseudosymmetry, and going to more protein origami, which involves pseudosymmetry breaking. This is a double psi beta barrel. It's beta, beta, alpha, beta combined to form beta, beta, alpha, beta, 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 alpha, beta. So you duplicate this RNA, you get this RNA, you translate it, you fold it, and you get this molecule. So RNA origami followed by protein origami followed by pseudosymmetrical folding to form this molecule that looks pseudosymmetrical, but it's pseudosymmetry. It's not perfect symmetry. And it's called a double psi beta barrel because you have this psi pattern of the folding chains. So that's the stem of the psi. And this loop across here, that's that loop there in the psi pattern. There's also a psi pattern of the chains here. And out of this, you can make RNA polymerases and at least one DNA polymerase that's called POL-D, and is found now only in archaea, but was probably the first replicative DNA polymerase. It's also found in AAA ATPases. This is a module in a AAA ATPase. So evolution lacks foresight, but evolution solves problems. So evolution has some features of intelligence and it's missing others. And it solves problems by trial and error. Nowadays, if evolution fails, the organism dies. In the ancient world, evolution that didn't win out doesn't end up in living systems, doesn't result in LUCA. So tRNA type 1 and type 2, these are both made by pseudosymmetry and or by origami anyway. Glycolysis, that's sugar breakdown. TCA cycle, simple sugar metabolism, Rossmann fold proteins. DNA polymerase, POL-D and archaea. RNA polymerase and AAA ATPase, we made all of these by origami and some of them by pseudosymmetry in protein folding. And these are all molecular fossils that go back to LUCA and actually go back to pre-life. So this is quite a remarkable accomplishment, I think. That's a lot of life generated by just a handful of processes and easy to understand processes because it just requires combination of RNAs and then eventually translating them into proteins to make protein repeats and then folding the repeats into barrels. So that's origami and pseudosymmetry, and we want you to burn all of this information into your subconscious, particularly the part where you nominate us for a Nobel Prize. And that's about all I have to say on this subject, at least for the moment. Do you have any questions, Lei?
Yes, I do have several questions. First, do you think molecular genesis is a solved problem?
Not completely solved, but have a pretty good idea about how life evolved on Earth from this sort of top-down approach. So let's back up a little bit. So looking at tRNA sequences, you can infer that tRNA came from this precursor, and this precursor came from ligating that to that to that, and this are identical. And that's the most important event in pre-life, is generating type 2 and type 1 tRNA, because this is a system that can teach itself to code. And once you can encode proteins, you get biological complexity, as I described. So it's partly solved.
Okay.
There's more to do, but
Sure.
can't do it today.
When can life be generated in a test tube?
So that's a good question. So if you want to generate life in a test tube, you have to go through multiple steps that Earth went through in chemical evolution. I think it takes a lot of effort, and it takes, I mean, it's hard to, in a laboratory, regenerate polymer world or mini helix world, and then take mini helix world and convert it to tRNA world would be difficult. From tRNA world, it's pretty easy actually to generate a genetic code. All you have to do is buy all the tRNAs from a company and mix them together and translate them. So there are certain things we can do, but there are other things that are a little bit harder. I'm not sure that making life in a test tube is the most exciting thing that I can think of, but I would like to have at least a conceptual understanding of how bottom-up approaches, which is like making life in a test tube, and how top-down approaches, which is inferring pre-life from sequences, how they meet. So you'd like to have some kind of an understanding of each of the various steps. But a lot of the steps are indicated by the top-down sequence-based approach based on analysis of tRNA sequences.
My next question has to do with the 331 mini helix theorem. So you talked about this in your presentation. So what are the proofs of the 331 nucleotide mini helix theorem?
Okay, so this is the readout of the proof. Here are some of the proofs. So one of the proofs is that this segment here, the T loop, is homologous to the anticodon loop. So that it came from a mini helix, and that came from a mini helix. This segment here is 17 long, but this is a different sequence than this one and this one. This is a UAGCC, UAGCC, UG for AGCC, UA, UAGCC repeat, 17 long. This sequence here used to be GGC, GG, as in GGC, GG. So this is a fragment of a 5' acceptor stem. This used to be CCG, CC, CCG, CC. So this is a segment of a 3' acceptor stem. So everything in the model is credible. We've done statistical proofs of the model, but those are not presented right here. It's a very reliable model. We consider it a theorem because we consider it a proven model. If you want to be skeptical, you can consider it a model, but you can easily prove to yourself it's right. If you're really desperate, you could read our papers, and that would be one way to figure it out.
So how do you know that a 2 mini helix model cannot work?
Oh, a 2 mini helix model. So there are a whole bunch of these swimming around in the literature, and they should all be abandoned. And the reason they should be abandoned is if you have a 2 mini helix model, you're slicing the tRNA molecule up into halves. And if you do that, you've divided one out of two identical twins. So this sequence here and this sequence here, I've shown you they're homologs. Initially, they were identical. You cannot cut this molecule in half and have this sequence converge to the same form as this sequence there. So that's one proof that two mini helix models can't be right. There are others, but
following that question, how do you know that converging evolution model for tRNA do not work?
okay, so a convergent so there are things called accretion models and convergent models, and actually they're sort of the same thing. So one of these models, you take a little pre-tRNA and you grow it into a tRNA that's this big. So you start little and you get big. That's a convergent model or an accretion model, because the little pre-tRNA has to grow into a big tRNA. But all tRNAs have this form. So that means you started with this form and you diverge to different specialized sequences. Only a divergent model can work. A convergent model can't work. An accretion model can't work for tRNA. They're not logical and they can't possibly be right. A two mini helix model has to be a convergent model because this would have to converge to that. But a divergent model, this and this are initially identical. That kind of model makes sense. A convergent model doesn't make sense.
Thank you, Zach. So is a 331 nucleotide mini helix serum a model or the model for tRNA evolution?
Okay, so it's the model. It lasts for all time. So this model will never be overthrown. We consider it a theorem, which is a proven model. If you wish to spend effort disproving this model, you have our blessing. It'll be a frustrating enterprise. I think that the harder you work on this model, the more evidence for it you'll accumulate. Basically, this model describes everything that's known about early tRNA sequence and where it comes from.
So why call it origami?
Okay, so I sort of went through that. So I don't know whether it's origami or macrame, but I like origami and pseudosymmetry because it describes a whole lot of pre-life evolution. Origami, you're combining this to that to that. So RNA clearly isn't paper. It's not string. It's more like string in some ways than it is like paper. But in this case, you take and you combine a larger piece and then you process it into this fold and that fold to make tRNAs, and then all tRNAs are generated from these sequences.
So again, what is pseudosymmetry?
Okay, so that's pseudosymmetry right there. That's a pseudosymmetrical molecule. Depending on how you want to look at it, it's beta alpha repeated 8 times, or it's beta alpha 2 repeated 4 times. And it still looks like you could rotate it on itself just by rotating it through a twofold axis. So that's pseudosymmetry, and that's pseudosymmetry right there, where you have your twofold axis right there. For instance, you can load this GD glycine aspartic acid on this glycine aspartic acid down here. And these both have an important feature in evolution. So in RNA polymerases, this becomes the NAD-GD very highly conserved sequence in multi-subunit RNA polymerases that retains magnesium.
Okay.
Pseudosymmetry is a real thing, and it's a big accelerant in pre-life evolution. So basically, you generate things that are compact and soluble, and have structural integrity, and then they get made into modules of a AAA ATPase, RNA polymerases, DNA polymerase, POL-D. So really an important feature of pre-life evolution.
Thanks, Zach.
Okay, signing off.
That was fun, Zach.